All right, folks, we should be pretty much closed out on the quiz for everybody at this point. So let's go ahead and get started. So what I want to do today is to talk a little bit about Hess's law of heat summation. I referenced it in the video, but I didn't define it for you. I figured we would actually do that today. So actually the equation that I gave you in last night's video to determine the delta H of reaction using delta H as a formation is actually a subset of Hess's law. So it's a nice pat equation you can use in certain instances to calculate a delta H of reaction, or to actually, if you have a delta H of reaction, calculate a delta H of formation for an unknown species. So we'll swing back around to that as well as time permits. But let's talk a little bit about Hess's law first. So what Hess's law allows us to do is to actually define a pathway. So what you'll remember here is that enthalpy, or H, is pathway independent, right? And we know that because it is a state function. And we know that it's a state function because we represent it with a capital H. Okay, so that was a couple videos back. So that's a nice thing to be able to utilize. So what this means is that I can choose any pathway I want to choose to calculate a delta H of reaction as long as it's a valid pathway. Okay, so where this comes into play is, what if I want to calculate a delta H of reaction for a reaction that I can't directly run in a bomb calorimeter, for example? So you guys will remember, I want to get delta H's of formation or delta H's of reaction. A lot of times I can run those reactions in bomb calorimeters to directly obtain those values of delta H. But what if I have a reaction I can't run in a calorimeter? Well, this is where Hess's law comes into play. What I can do is I can summarize that reaction in terms of other reactions that I can sum together, whose delta H's I can actually measure using a calorimetry experiment. All right, so that's the situation that we want to take advantage of here. Now, the easiest way to actually demonstrate Hess's law is to look at an example of it. So let me just show you the givens here in example 1. And this is the typical setup for a Hess's law kind of problem. Okay, so let's just look at it real quick. So I want to use Hess's law to determine a delta H of reaction for some reaction. I'm going to refer to this as the target reaction. Okay, this is the reaction I want to get the delta H for. Okay, now, if you notice, it's not a combustion reaction. Okay, so it's a reaction involving a hydrocarbon, C3H4, combining with hydrogen gas to give me C3H8 gas. Okay, so this may not be a reaction I could just simply run in a bomb calorimeter. All right, but what if I could somehow get back at that reaction through a series of given reactions that I can run in calorimeters? Okay, so for example, look at the 3 given reactions. Notice that they're all combustion reactions, right? So these are reactions that I can run in a calorimeter and determine a delta H for from an experiment. All right. So the idea here is I would like to be able to take these given reactions and somehow sum them together along with their delta H's to give me the delta H of reaction for the target reaction. Okay. So this is really kind of a fun thing to do, because what I'm doing here is I'm taking these 3 given reactions along with their given delta H values to see if I can somehow rearrange them, manipulate them in some ways that when I sum them together, I can get back to the target reaction. So I want to be able to get the sum of the reactions as well as the corresponding delta H's to do that. Okay, so it's kind of like a little puzzle we have to put together. All right, so here's how we go about doing it. All right, so what I'm going to do is I'm going to use the target reaction essentially as my target. That's what I want to hit. Okay, so I'm going to start looking at individual parts of the target reaction, and I'm going to try to find those parts in the given 3 reactions. And let's, for example, look at the C3H4. Okay, so that's the first one we'll click out of the way. So I'm looking down here in the given reactions for C3H4. Oh, I found it. It's down here in reaction 2. I'll put a little check mark over it. Now notice that it shows up in the given reaction as a reactant. okay? Notice that it's also a reactant in the target reaction. Notice that in the target reaction, I need 1 mole of it. Notice also in the given reaction, I also need have 1 mole of it. Okay, so what that means is when I get down to my summation here, so I'm going to rearrange and look at these equations, I'm going to leave that reaction exactly the way it's written because that's how I'm going to use it. So let's go ahead and just write it here so we see how it all sums together. C3H4 in the gaseous form plus 4O2. Okay, and that's going to go to 3 CO2s and 2 H2Os. All right, and that's a liquid. Now, since I did not manipulate the reaction equation in any way, what does that suggest about the delta H? Well, it tells me I don't have to do anything to the delta H. So my delta H, I'm just going to leave as minus 1937 kilojoules. Okay, and that's understood to be per mole of reaction. All right, so let's go to the product side next. So the product I need is the C3H8. So I'm going to look for a reaction down in the givens that has C3H8 in it. Oh, and there is one. If you look down at the third reaction, there's the C3H8. Okay, everybody see it? Now here's the problem. Notice that in the given reaction, it shows up on the reactant side, but I need it to be on the product side. So what am I going to do to the given reaction? What do I need to do to make that show up on the product side? What do you guys think? Well, how about flip the reaction? Why can't I do that? I can flip the reaction. In other words, make the products the reactants and the reactants the products. So let's write it that way. So this is my first one where I have to do a manipulation. So I'm going to write it the way I need it to be. So that's 3CO2 gas. Okay. Oh, sorry. Yep, that's the right one. Plus 4H2O, right? Okay, and what else do I have? I get the C3H8. Now it's on the side of the reaction equation where I need it to be, right? And I still have my 5 O2s. Okay, but here's the thing we have to remember. If I flip a reaction, what do I have to do to the original delta H that's given? Okay, here's the rule. If I flip a reaction, all I have to do is change the sign of the assigned delta H. So notice in the original C3H reaction, as given, the delta H is minus 2219 kilojoules. But if I flip the reaction, all I'm going to do is change the sign. So now that's going to become a positive 2219. So that's an important thing to remember is every time we manipulate a reaction, we have to think about what manipulation we have to do with the delta H. Okay, does that make sense to everybody, what I did there? All right, so that takes care of those two things. Now let's go back to the other reactant. I need 2 H2s. Okay, so do I actually see a reaction that has an H2 in it that I haven't used? Yeah, it's right up here. It's that very first given reaction that I put a check mark over. Now here's the thing. The H2 is on the correct side of the equation. It's a reactant, but notice that the moles don't match up. In the given equation, I have 1 mole of H2, but in the target equation, I need 2 of them. So what does that tell me I have to do? Well, it tells me I have to take the original equation and multiply by 2. Okay, so I'm going to take that original equation and multiply everything through by 2. All right, so let's do that. So it's going to give me 2 H2s. Okay, 2 times a half is 1, so that's O2. All right, and then I need 2 H2O liquids, right? Now, what do you think I need to do to the delta H if I multiply the reaction through by 2? What do you think I need to do to the given delta H? Anybody got any ideas on that? What would sort of be the obvious thing to do? Well, how about multiply it through by 2, right? So we can do that. If we multiply a reaction through by 2, We'll multiply the delta H through by 2. Do I need to change its sign? No, because I didn't flip the reaction. So this is going to be 2 times whatever the given delta H was, which is minus 285.8. Oops. All right. So ultimately then, what I want to do is I want to sum up the reactions, but I also need to sum up the delta H's. So whatever I do with the reaction, I'm also going to do with the delta H's. Now here's the deal. When I sum these reactions up, and this is kind of the check we have to do, we have to make sure that they actually sum up to the original target reaction, which is up there at the top. Okay, I'm going to try to leave it on the screen so you guys can see it. So let's see. Looks like we can probably cancel some stuff out. So we're always going to look for stuff to cancel out first. So I see 3 CO2s on the left, which can cancel with 3 CO2s on the right. Okay. Now I also look like I can get rid of some waters here. So I have 2 H2Os, 2 H2Os. Those sum to 4, so those cancel with 4 H2Os there. Okay. Now, is there anything else I can get rid of? Well, let's look at some oxygens. Looks like I've got 5 O2s on the right and then 4 on the left plus 1 more, which is 5. So it looks like the O2s are going to cancel each other out. And what am I left with? I'm left with C3H4, 2H2, and C3H8. Is that what I get for the target reaction? Yeah, that's the target reaction back again. So let's write it. So I have C3H4 gas plus 2H2 gas. And that's our check, that we can get the original reaction back again when we sum up our manipulated reactions. So that's C3H8 on the product side in the gaseous form. So what do we do with the delta H's? Well, we do the very same thing. We just sum them up. Okay, so I took the 2 times minus 285.8, got a number, added that to 2219, and then added that to a negative 1937 kilojoules. And when I do that, I end up getting minus 290 kilojoules. Okay, so that's actually going to be the delta H of reaction for my target reaction. And I got it from known delta H's of known reactions that I could then manipulate. Okay. So Hess's Law problems all work the same way. This is going to be the format you're always going to see for them. All right, any questions about how to set up a Hess's Law problem? Does this kind of make sense to just see the steps that we need to go through? Okay, good. And it's a fun thing to do. Like I said, it's like putting a little puzzle together to make it all work out. So it's kind of a fun thing to do. Now, let me go back to another example, and this is more in line with what we were doing in the video last night, where we were actually talking about how to get a delta H of reaction from that nice pat equation that I gave you, okay? So this is kind of working from that standpoint in order to determine a delta H of formation. Okay, so I want a delta H of formation of carbon tetrachloride or CCl4, okay? And I'm at 25 degrees C in 1 atmosphere. And I have to be there because those are the conditions for standard state, right? And in this case, I've got a reaction and I'm given a delta H of reaction for that reaction. It's minus 397.3 kilojoules per mole. And what I'm after is the delta H of formation of the carbon tetrachloride. That's what I want to get. Now, normally in a problem like this, I'd have some given delta H of formation values. So I'm going to write those here. And these are standard delta H of formation values. You can look them up in a table, but the nice thing is with Chem 101, they would actually have them in a nice tabular form for you right there in the problem for you to use. All right, so the delta H of formation given for the CH4 is minus 74.87. By the way, these are all going to be in terms of kilojoules per mole. All right. For chlorine gas, it's 0 kilojoules per mole. And then the given value for HCl gas is minus 92.31. And that's in kilojoules per mole as well. Okay. So you can kind of see what we've got here. We can set up an algebraic situation where we have one equation and one unknown. Okay, so what's our starting point? Well, our starting point is going back to that nice equation I gave you in the video. And here's what it says. it says for any reaction, I can write the following. I can say that the delta H standard state for any reaction is equal to the sum, remember that's the summation sign from last time, of N times the delta H of formations, which are given there, of all the products, minus the sum of N times the delta H of formation standard state of the reactants. In other words, everything to the left-hand side of the arrow. All right. Now remember, the N here in both cases turns out to be the number of moles. In other words, that's the stoichiometric coefficient that we have in the equation. So for example, in the CH4, that's 1 mole. But for the Cl2, oh yeah, I need 4 of them. Okay. For CCl4, I'm 1. For HCl, I got 4 of them. Okay. So it's just the number of moles in the stoichiometric equation. That's what goes in there for N. All right, so now what I can do is I can kind of use the equation and plug in what I know. So I know what the delta H of reaction is. That was given for the reaction. That's minus 397.3. I'm just going to leave the units off for now. We know they're all in kilojoules per mole. Okay, so now let's summarize what we've got for the products. All right, so carbon tetrachloride is the one I'm trying to get. So that's really going to be 1 times X. I'm just going to call that X because it's the variable. That's the delta H of formation I'm trying to get. Okay. Now, what else do I have there? Now, I'm supposed to sum that to, oh yeah, I've got HCl in there, but I got 4 of them. So that's going to be 4 times the delta H of that, which is minus 92.31. Okay, so I think I've got all of the products taken care of at this time. So now let's go back and subtract from that all of the reactants. Okay, for the CH4, I've got 1 mole of it times minus 74.87. Okay, and then I've got added to that 4 moles of the chlorine times 0, right? So I'll put that in there as well, just to be proper about it. All right, so now what we can kind of do is recognize that this whole thing, without actually having to do any math, is just minus 74.87. Okay, and then what else do I have? Well, this turns out to be, let's see, 4 times minus 92. Is that minus 369.24, I think is what I've got. Kilojoules per mole. Okay, so you can kind of see what we're going to end up here with. Let me just sort of summarize it. Minus 397.3 is going to equal to, we'll just call that X because 1 times X is just X, minus 369.24 kilojoules. And then we've got additive, and then we've got, let's see, minus a 74.87. But watch out, I have a negative times a negative in there. So I have to remember that that negative distributes inside. So that becomes what, plus 74.87. Okay. So now you can go ahead and just collect like terms at this point. All right. And if you do this, the delta H of formation, which is just your X, I'm just getting X by itself, is minus 397.3. Okay, and then I take the other stuff to the other side, plus 369.24 minus 74.87, just getting everything on the same side. And then when you work this out, my math tells me that's going to be minus 102 kilojoules. Now keep in mind that this is per mole of formation of the CCl4. And that turns out to be a delta H of formation of that species, okay? So that's another situation that sort of ties back nicely to what we did in the video. And it's just a nice pat algebraic expression. So we have a few minutes left, not many. let's just run back and just see if we can real quickly run through a Chem 101 exercise here. And again, you don't have to stay late or anything for this. Just see how far you guys get. This is just a Hess's Law one. Matter of fact, you can just pick the problem you want to do. You probably have time to maybe do one problem. So you can pick any of the three. Number one's a good old standard Hess's Law problem if you want to try that. And then 2 and 3 are kind of more like what we just did here in example 2. All right, folks, looks like we're about the end of class here. Feel free to continue working on these if you have time or desire to do so. Practice up, be ready for regular 5 for 5 on Monday and move ahead to the next video. So have a wonderful weekend and we'll see you guys on Monday.